in the previous classes. Yesterday we have stated what is Parseval identity and what are the results related to Parseval identity. Today we shall start our topic with the relationship between Fourier transform and Laplace transform. So let us start with that relation between Fourier and Laplace transform. Now for this we need to take f of t is a function of variable t, that is e raised to power minus of st into g of t, and the function defined for t greater than 0, and it is the 0 if t is less than 0. Now then the Fourier transform of f of t is always equal to Laplace transform of g of t. So this is the relationship between Fourier transform and Laplace transform. Capital F stands for Fourier transform, capital L stands for Laplace transform. How we can prove this result? So Fourier transform of f of t can be defined by definition integration minus infinity to infinity e raised to power st into f of t dt. Now you just see this is the integral, this is the value of the function with the interval 0 to infinity, and this is the value of the function with the interval minus infinity to 0. So you can break the interval into two, and you can take the value of a function f of t in the interval minus infinity to 0. F of t is 0, and in the interval 0 to infinity, the value of f of t is equal to e raised to power minus st into g of t dt. Now this integral will vanish. Ultimately you will have e raised to power, you can take minus common, and inside is s minus iota s into t into g of t dt. Now you just see this is a parameter, s is a parameter. So if s is a parameter, then s minus iota s will also be a parameter. So we can name it as a new parameter, small p. So ultimately we can take s minus iota s is small p. So that is e raised to power minus pt into g of t dt. And if you recall the definition of Laplace of f of t, that is the definition 0 to infinity e raised to power minus st f of t dt. So this is the Laplace of f of t, standard definition of Laplace. Here s is a parameter. We can change the parameter also, because the parameter may be any. This is just a notation. So in place of s, it will take p, then it doesn't make any difference in the value of the integral, because we are to integrate with respect to t and substitute the limit. So there will be no difference in the values of these two integrals. And obviously it will also be a Laplace of f of t. Now by using this definition, here e raised to power minus pt is there, but in place of ft we have gt. So by the definition, that should be equal to Laplace of gt. So this is the relationship between Fourier transform and Laplace transform. Always remember that Fourier transform of a function of t is equal to Laplace transform of another function gt. And where does GT comes from? GT comes from f of t, because f of t is equal to the exponential multiplication with GT. This is very important relationship we have, and now we have a residue theorem related to this. Residue theorem is helpful for finding out the inverse Laplace transform. Earlier we have got the inverse Laplace transform by the method of partial fraction, and we have done it with the partial fraction method and convolution theorem. But now we will do that, how to find out the Laplace inverse transform with the help of residues. So this is also very important thing, and this method is also helpful for finding out the inverse Laplace transform. So the question is, you need to find out the inverse Laplace transform of the function s minus 1 upon s minus 1, and that is s square plus 1. We need to find out, and by the method of residues only. So because the amplitude or the modulus of this function, the modulus of this function is approximately the same, and that will be 1 over s cube, and that I will take the maximum value approximate to that, and this maximum value will be the modulus value approaches to infinity. So it should always be true, and we should approach to 0 even, because it will approach to 0 when as modulus approaches to infinity. It will always be there. There is no doubt about that. So we shall find out the inverse Laplace of this function. This one. This is f bar x actually, and the inverse of f bar s. It is a function of parameter s. So you will be able to find out the inverse Laplace transform by the method of residue. So that will be equal to sum of residues of. Now we need to take the function denominator will be same as there in f bar s, but only you have to multiply with e raised to power x s. This is the method. So add the poles, and what are the poles and how to find out the poles. Poles are very important, and how will you find out the poles? By putting the denominator value equal to 0. So if you put a denominator equal to 0, you will get s is equal to 1 and plus minus eta. So the poles are s is equal to 1 and plus minus eta. So what does it mean? That will be the sum of residues. The residue at s is equal to 1 plus residue at s is equal to delta plus residue at s is equal to minus 1. Sum is there. Addition we need to do it. So let us find out the residues. So you just name it as number 1. After finding out all the 3 residues, you will just substitute the values here and get the answer. It's very easy. And how to find out the residue? Residue at s is equal to 1. That is the limit s approaches to 1, s minus 1. This factor comes from this s equal to 1. Suppose at s equal to minus 1 is there, then limit s approaches to minus 1, and there will be s plus 1 into the same function. The function is e raised to power x s minus 1 s square plus 1. So this factor can be cancelled. You can substitute the limit s approaches to 1, that is e power x, and the 1 square is 1 plus 1, that is 2. This is your first residue. Similarly, we can get the second residue and s is equal to iota. The limit s approaches to iota, that is s minus iota, e raised to power xs upon s minus 1. Now this factor can be factorized like this: s minus iota, s plus iota, by using a minus b, a plus b, because we have to cancel the factor. For the limit s approaches to iota, you will get e raised to power iota x. That will be iota plus iota to iota into iota minus 1. This is your second residue. And the third residue, how to find out the third residue? The third residue will be s equal to minus iota. Now, we will find out here, but simply you can also do. This is the residue for s is equal to iota, and now we have to find s equal to minus iota. So you simply change iota to minus iota in this. So that is minus 2 iota, and in the denominator minus iota. That will be e raised to power minus iota x. That will be 2 iota into iota plus 1. So this is the third residue. Now you can put the values in equation number 1. This one. You can put the values in 1 and get the answer. And no doubt you need to simplify the values. E raised to power iota x, 2 iota, iota minus 1, e raised to power minus iota x upon 2 iota, iota plus 1. Now you just simplify it more and get the solution. We will simplify it. I leave it as a assignment. One more important point which I have to remember. Suppose there are poles like this, s is equal to 1 and 1 in this case. Or you can say that here your f bar s is like this. F bar s is 1 over s minus 1 square, and here is s square plus 1. And clearly the poles will be 1 and 1 and plus or minus iota. So there are 4 poles or 4 roots of the denominator. Now 1 and 1 are multiple poles, and multiple poles and are similar. So how to find out the residue in that case? The method is a little different. Residue at s equal to 1, limit s approaches to 1, s minus 1 whole square into d by ds first order, because pole multiple pole is there and multiple pole of order 2. Order 2 means it comes twice. So if it comes twice, then there will be first order derivative, and if it comes thrice, 3 times, then there will be second order derivative. So always remember that is e raised to power xs from s minus 1 square, that is s square plus 1. And one more thing also, dds will come here. This one, this will be the factor. But how to write down dds? This is the way to write down dds. S minus 1 whole square equal, and this factor will be cancelled. Now, first of all, you will find out the derivative with respect to x with the u over v formula, and then substitute it. So this is the way to find out the residue at multiple poles of order 2 or order 3. So by this way, you can simplify and find out the inverse Laplace transform. So let us come to the application part. that will be the applications of Fourier transforms to solve boundary value problems. So this is the application part. And boundary value problems will be the partial differential equation, whether it is an equation or it is a free equation. These are standard. Equation and free equations are standard. Now, some important point to note down. First point is, if in a problem the value of uxt at x equal to 0 is given. This is the value of the function u. U is a function of two variables, x, that is the displacement function, and t is the time. So that is uxt at x equal to 0 is given. Then we will use infinite sine transform. This is the way to apply the transform. And if, now this is the second condition, if the derivative condition is given, that is the del u by del x, u is clearly a function of x and t. And if the derivative condition at x equal to 0 is given, then you apply infinite cosine transforms. The third important condition is if the boundary conditions are given, u0t and u then we employ finite Fourier transform, not infinite. Remember, finite Fourier sine transform we shall employ. And if again the fourth one is the derivative condition is given at x equal to 0 and then we employ finite cosine transform. So this is the way that which transform we will apply. You must remember these these 4 points. That we are to employ infinite sine transform, infinite Fourier sine transform, and infinite Fourier cosine transform. Fourier transform is there. We are to employ finite Fourier sine transform and finite Fourier cosine transform. So this is very important to know that we are to apply which transform. Let us do an example. And in the example, we shall have the question is determine the temperature distribution in the semi-infinite medium. And the semi-infinite, whenever it is said that it is a semi-infinite medium, then it means x is greater than or equal to 0. What does it mean? That is 0 to infinity. And infinite medium, when the end x equal to 0 is maintained at 0 temperature. The medium is like this. We don't know which medium we have. We don't know the medium or the material or the type of material we have. This is the end x equal to 0. Obviously, it will have some end. But we are saying that that is semi-infinite. So we don't know the length of the end. So we have given that at x equal to 0 and this one, the temperature is 0. The temperature is 0 meaning u is equal to 0. So this is the condition we have. u0t is 0. This 0 stands for x equal to 0. Okay. And the initial distribution of a function is fx. Initial, whenever they say that initial, it means at t is equal to 0. So ux0 is equal to a function. And this is given to us these two conditions are there. And because we are talking about the temperature function, so you have to assume that uxt be the temperature at any point x and at any time t. So we have to solve the heat equation. So later to uxt, we should have heat equation del U by del T is c square, del square V by del S square. So this is equation number one. This is the standard heat equation. Clearly U is a function of x and t. Because derivative of U are with respect to x and with respect to t. And these are the conditions. Number 2 and number 3 are the condition. Now if you see what is given to us, we have given the value of u xt at x equal to 0 is given this one. And you just see the first point which we have noted, that uxt at x equal to 0 is given, and we need to apply infinite Fourier Sine transform. So you apply infinite Fourier Sine transform to equation 1. So you can say apply infinite Fourier Sine transform. You are going to as a two and of 1. What will you get? So this will be the that is another Fourier Sine transform of del U by del T is equal to c square is a constant. Cannot take the Fourier transform option. So it can be taken out by linear Fourier Sine transform of del square U by del square. As we know the formula of the Fourier transform, the derivative for the variable x will transformed to the parameter s. So there is no role of t variable. It can be written like this. That is dgt, and the Fourier transform, Fourier Sine transform of u will exist. So Fourier Sine transform of f of x. If you remember the definition, that is fsx. So Fourier Sine transform of uxt, this one, that is u or uxt, both are same. U is a function of x and t. So what will be this? There will be u as dot. So you can write down that is u as dot. And here it is a function of s and t. So you can write down in both ways. So that would be c square. We will use the derivative method as we have used in Laplace transform. This is the second order derivative term. So we will start with s u 0t minus s square u s1. You always start with s and you go up to which order term we have the derivative. Derivative of the second order, then we will go up to s square. So that is the dus bar by dt. What is the u0t? U0t is 0. We just see equation number 2. So from equation number 2, if you take the Fourier Sine transform of u0 of t, on the right hand side, Fourier Sine transform of 0 will be 0. So what about that? Fourier Sine transform of u0t will be 0. Ultimately, this value will be 0. And constant should be written first. It should be written like that: c square s square, and you can write in the equation like this. That will be solve the equation by writing down its auxiliary equation, and that will be d plus c square s square into d plus bar equal to 0. You can change d to some another parameter small m also. We have done in the previous semester. So you can also write down d as it is. There is no problem. So this is the variable and this minus c square as square. So automatically we can be able to we can find out the value of the function d plus square is equal to constant. The constant a is there, that is e raised to power minus c square plus square e. And clearly, that is this us bar, and the us bar is what? That is a function of s and t. A e raised to power minus c square plus square, and we can name it as, we have named it 1, 2, 3. Now we can name it as a flow. So from condition number 3, this one, we can solve this condition also. From equation number 3, by taking Fourier Sine Transform, we will have us bar s 0 will be f bar s by taking its transform. And what is this value? This is the value at t is equal to 0. So ultimately we can take or put e0 in this equation forward. So we will have e raised to power minus c square s square into 0. So e raised to power 0 is 1. So constant value is equal to this. And what is this? This is f bar s. So ultimately the constant a comes out to be f bar s. So therefore we can get u s bar s t. What is the value of t? That is f bar s e raised to power minus c square plus equals. So this is the Fourier Sine transform of the given differential equation. And because we want to solve, and what we want to do, we want to solve this differential equation. Solve means you have to find out the value of the rectangle variable. U is a function of x. So this is what we want to do. So we want to find out the value of u xt. So from this, if you want to find out the value of u, you just need to take inverse Fourier sine transform. So taking the inverse Fourier sine transform, we shall have u xt, and the formula is 2 upon y, 0 to infinity, and that will be f bar s e raised to power minus c square s square d into sine of s x ds. So if you have the value of this function, and you have this function, you have this function, but you don't know the value of this. So if you have the value of this, probably you will be able to find out this integration. So that integration will be the value of the required solution. But here, because we don't know the value of function fx, as it was given as a function fx in condition 3, so it means you have to stop the solution here. So this is your required solution. So this is very important aspect to find out the solution of a partial differential equation. So I will stop here. so that you revise the questions related to this. I will go to the next part in the tomorrow's class, and I advise you to do some questions at home with the help of this analytical exam. So thank you very much. Thank you.